This video podcast is going to be about sulfur chemistry and is part of the pharmaceutical chemistry first year unit. Known drugs, a selection of known drugs include chlorpromazine, an antipsychotic drug which acts at G protein coupled receptors in the brain. And this compound contains a cyclic thioether. That's a very general name. You'll learn a little bit more about this type of ring system in a latter part of the course. When you do heterocyclic chemistry, this is actually a heterocycle, but it could be broadly classed as a cyclic thioether in terms of its behavior. Sulfur methoxypyridazine is an antibacterial, and it's a dihydrofolate reductase inhibitor, part of a broader group of compounds called the sulfonamides, and that's because this contains a sulfonamide functionality. This is the sulfonamide group here. You may be familiar with carboxamides or carboxamides, the carbon-based amides. This is the sulfur-based system. We'll learn a little more about those later on. This is Viagra. Viagra is a vasodilator. It's a phosphodiesterase inhibitor, and Viagra, a drug that was found by serendipity, a very chance occurrence of a clinical observation, led to a major selling drug. This compound is a sulfonamide, and we have the sulfonamide again. The sulfonamide functionality is here. Omeprazole, slightly old drug now and being superseded by further members of this class, the prazoles. This is an anti-ulcer drug and is a big selling drug. It is an ATPase inhibitor, works at a proton pump in the stomach, and this is a sulfoxide. To all intents and purposes, that looks very similar to a carbonyl bond, but we'll find out that it has slightly different bonding properties than a carbonyl. Natural chemicals that occur that contain sulfur include cysteine, an amino acid. We've met that in the cells to systems unit. Lipoic acid, which is an enzyme cofactor, and lipoic acid has a heterocyclic ring with a disulfide as part of that ring system. Slightly unusual structure for nature. This is allicin. It's a pungent odour from garlic. When you smell garlicky breath, this is one of the reasons why. And some people metabolize allicin differently to others, which is why when they metabolize it well, the garlic odor doesn't reside on their breath, stay on their breath. If you don't metabolize it particularly well, you smell garlicky for a long time. This is 6-APA, which is an amino penicillic acid, and this is a penicillin nucleus. Again, notice it's the sulfur is part of a heterocyclic ring system. This is quite an unusual chemical because it has a four-membered ring in it as well, which is quite rare in nature. Okay, let's take a look at the sulfur chemistry, and to do that we need to consider the electrons that are available in sulfur. Sulfur is in the same functional group, group 6A, group 16, as oxygen, and oxygen utilizes electrons in the ground state configuration 1s2, 2s2, 2p4 for its covalent bonding, or for its bonding. and here's an energy level diagram taking into account these electrons, and you notice that oxygen has 2 free electrons available to it for bonding to 2 other atoms that will give it electrons to complete its shell in its covalent bonding. Sulfur has its level 2 subshell complete, but can utilize its level 3 electrons in a similar way to oxygen, and some d orbitals are nearby in energy. So let's take a look at those. So here we have our oxygen core, and that's a complete inner core electron configuration, inner valency. These are outer valency electrons, and they mimic the structure for oxygen, but at the level 3, and that's why sulfur behaves comparably to oxygen in some of its covalency. However, it does have, in very small striking distance, a set of d orbitals that are going to influence sulfur's chemistry and make it slightly unusual for that group. Since sulfur and oxygen are in the same group of the periodic table, you would expect their covalent chemistries to be very similar, and this is the case. So where one can visualize oxygen chemistry, sulfur chemistry should follow pretty closely. So thia or thio analogues of alcohols, carboxylic acids, esters, amides, ethers, etc. can exist alongside the oxygen analogues, and synthetically often they can be made in similar ways, but you've got to be a bit careful because the sulfur containing compounds have varying stabilities. Thioaldehydes and thioketones, which are the sulfur analogues of aldehydes and ketones, are, for instance, or can be particularly unstable, which can be at odds to the oxygen chemistry. So here we have some common sulfur analogues, and you can see where sulfur can readily take the place of oxygen. So in this series we've got an ester. We have a sulfur group substituting for that oxygen here, or a sulfur for this oxygen and leaving that one alone, or indeed we can substitute both positions for sulfur, and to synthesize each of these you would have to take different synthetic routes to ensure the correct structures made. Amides, we've met amides before, and thioamides can exist, which is the sulfur containing analogues. And then ethers. Quite often first year students can get ethers and esters mixed up because of their similar nomenclature, but this is an ether, and this would be a thioether, the sulfur analogue. So we're going to have a quick look at nomenclature. So alcohols and thioalcohols, sometimes called mercaptans, which is a slightly old nomenclature but still is out there in the literature. Ether and thioether, which is also referred to as a sulfide. Thioether is a slightly better name because sulfide can get confused with metal sulfides, but it's an older nomenclature. Aldehydes and ketones, thioaldehydes and thioketones as previously mentioned. Peroxide and disulfide. Now peroxides you don't come across that often in chemistry before you come to university, other than you will know that of the peroxide linkages where R and R1 are hydrogen, for instance hydrogen peroxide, and the disulfide system exists, and the organically substituted disulfide system exists. esters and thiol esters, where the alcoholic part has been substituted, and then esters and thione or thionoesters, where the own carbonyl type oxygen has been substituted. So thiols, what sort of indicative chemistry do we have for thiols? Well, thiols can undergo mild oxidation. We've met this sort of chemistry before. In fact, we met it when we talked about the properties of cysteine as an amino acid. But general thiols can undergo this type of chemistry as well, and oxidation will lead to disulfide formation, and disulfides in general can be cleaved readily under reducing conditions to go in the reverse direction, and there's a link to some of that chemistry through the PowerPoint. Cysteine can be oxidized to cysteine, and this can occur through the amino acids, but it also can occur within proteins where the polypeptide backbone is continued. So this would be maybe a protein structure twirling around here from an amino end to a carboxyl end. And here's an example. Ribonuclease. In fact, ribonuclease, if you look at this color-coded diagram, has yellow patches in it. Each of these are disulfides. There's one hidden there and one here. And ribonuclease, in fact, has been studied as a protein that undergoes tertiary structure formation via various disulfide intermediates to lead to this final structure. And we mentioned the role of disulfides when we talked about how proteins form their three-dimensional structure in the cells to systems unit. Thiols can be oxidized by chemical oxidation. Chemical oxidation can be over-oxidizing, and standard oxidizing agents can over-oxidize thiols. So, for instance, Jones oxidation by sodium dichromate and acidic conditions, or potassium permanganate can oxidize thiols to sulfonic acids. Other agents can do this chemistry as well. For instance, sodium hypochlorite, which is a component of bleach, and hydrogen peroxide itself can be used to fully oxidize a sulfonic acid, encourage it to oxidize fully. Now, what's interesting here is that the reduction of a sulfonic acid to a thiol with standard reducing agents is actually quite resistant. The process is quite resistant to normal reductants that you may have come across, such as lithium aluminium hydride, sodium borohydride, the catalytic metals and hydrogen all cause a bit of a problem for sulfonic acids going to thiols. It's not impossible, but it's not the rule that they reduce well. So you can take a bit of a sidestep. One can form an acid chloride, a sulfonyl acid chloride from sulfonic acid by treating it with PCl5, a classical chlorinating agent, phosphorus pentachloride, and then this activated, more reactive sulfonyl compound is more prone to reduction by things like lithium aluminium hydride, etc. And so you can take a bit of a sidestep to do that chemistry. Chemical oxidation of structures such as thioethers can lead to additional chemistries such as sulfoxides, and cold hydrogen peroxide can induce this oxidation. Hydrogen peroxide acts as an electrophilic oxidizing agent, and the electrophilic components of H2O2 will attack the nucleophile, nucleophilic sulfur, to add an oxygen to that system. This is known as a sulfoxide. Now, sulfoxides can be drawn with a resonance structure. If you notice the chemistry of the sulfoxide here, because we've added a covalent bond to a divalent, normally divalent sulfur, that the consequence is that that sulfur has a positive charge. A monocovalency to oxygen, when that oxygen has a complete electron shell, means that the oxygen will be negatively charged. So this is effectively a zwitterionic type structure, but you can actually draw a more covalent representation of that molecule, and there are some reasons why that might be possible. Sulfoxides are potentially chiral compounds, but they're also tetrahedral, and they're tetrahedral because of the nature of this, the bonding around the sulfur. The multiple bond character, the double bond character that's depicted here, comes about not because of a carbonyl like sp2 hybridization around the sulfur. In fact, the sulfur is sp3 hybridized, but the double bond comes about because of a donation of a pair of electrons from the oxygen's p orbital, which is a pi-type orbital, into a d orbital that's empty. Remember, we mentioned the d orbitals, and the d orbital can accept electron density from the oxygen, and this is the definition of a covalent bond. If you can move electrons between one atom and another, you can induce covalency, and in fact our second covalent bond comes about because of this type of interaction. And sulfur uses this chemistry in the multiple bonded compounds we've already seen on the previous slides. Thioethers can be oxidized more fully to sulfones. You notice that hydrogen peroxide is being used to do that reaction again, but in this case it's hot conditions, and that over-oxidizes the thioether to what's called a sulfone. And there's a link to that chemistry. Sulfones can also result from oxidation biologically by enzymes in the body, various enzymes in the body that oxidize drug substances, particularly hydrophobic drug substances, in attempt to eliminate them from the body as a foreign compound. And metabolism of this particular drug, which is thioridazine, comes about through quite a complex set of steps. You can get monosulfoxides formed, either sulfurs that are present in the parent compound. Now, what's interesting is you tend not to get the disulfoxide where both sulfurs have oxygens on. You either get one or the other, which is quite an interesting observation. But what you do get from these compounds on further oxidation is the fully oxidized disulfone. That's noticed. So when you look at the metabolism of this drug, and you look at maybe using chromatographic methods such as HPLC, GC, HPLC or GC, you can see these two sulfoxides and this sulfone, but not a disulfoxide. Ester chemistry. We can form thioesters from a reaction of an acid chloride with the thiol. So X would be Cl, for instance, in an acid chloride, or in fact an acid anhydride, like the chemistry you've met within paracetamol chemistry practicals in the pharmaceutical chemistry practical unit. And there's a link to that chemistry there. We can also convert esters directly into thione esters. This is a bit weird, because this can be achieved by a very peculiar reagent known as Laurson's reagent. And Laurson's reagent actually is a sulfur transferring agent with a most peculiar phosphorus and sulfur cluster of atoms here, and in fact one of these sulfurs gets transferred to the carbonyl. The oxygen gets displaced in quite a complex mechanism to attach sulfur here. It does not influence the chemistry of the oxygen, which is why it's an interesting reagent. It actually accesses the carbonyl and causes sulfur to be introduced, replacing the oxygen of the carbonyl. Amide chemistry and thioamide chemistry have parallels. We already met the fact that we can have sulfonyl halides, and sulfonyl halides can react with amines to give sulfonamides, as we saw in the first slide when we talked about drugs. And this chemistry is relatively reminiscent of the carbon-based chemistry. And if you're not so familiar with that, go back to carbon-based systems, carboxylic acids being converted to amides to revise that material. Sulfonamides, such as sulfanilamide, are antibacterial. And in fact, sulfanilamide was one of the first synthetic antibacterial compounds to be investigated for its antibacterial action. And it gave rise to a whole family of drugs broadly known as the sulfonamides that are antibacterial.